Welcome to this video on light waves. Today, we will explore the concepts of refraction, Snell's law, and total internal reflection as part of our Year 11 physics curriculum. By the end of this video, you will understand the phenomenon of refraction, how to apply Snell's law, calculate critical angles, and describe the principles and applications of total internal reflection. Have you ever wondered why a pencil in a glass of water looks bent? This happens because light changes direction when it crosses the boundary between different media. It is not an illusion of the object, but a change in the path of light itself. Refraction is defined as the bending of a wave as it passes from one medium to another at an angle. For this to occur, light must strike the boundary at an angle. The two materials must have different optical densities, and the speed of light must change. The physics of bending involves a change in speed. As light enters a different material, its speed and wavelength change, though the frequency remains constant. This speed change causes one side of a wavefront to slow down before the other, pivoting the ray's path. You can visualize this with the car on sand analogy. Imagine a car driving from a paved road onto sand at an angle. The wheel that hits the sand first slows down, causing the car to pivot toward the slower side. Light behaves in a similar way. To describe these paths, we use specific terminology. The normal is an imaginary line perpendicular to the surface. The incident ray is the incoming light. The refracted ray is the ray after it crosses the boundary, and all angles are measured from the normal. There are general rules for refraction. Light moving from a fast to a slow medium bends toward the normal, while moving from slow to fast bends away. If light enters along the normal at 0 degrees, it changes speed but does not bend. When light passes through a rectangular glass block, it experiences double refraction. It bends toward the normal upon entering and away by the same amount upon exiting. This keeps the light parallel to its original path, but shifted to the side, a phenomenon called lateral displacement. Now, let us look at the mathematics behind these phenomena. We can quantify the bending of light using Snell's law. The first law of refraction states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. The second law, or Snell's law, establishes that for any two media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. This constant is known as the refractive index of the second medium relative to the first. The refractive index, denoted by n, measures how much a material slows down light compared to a vacuum. It is calculated by dividing the speed of light in a vacuum c by the speed of light in the medium v. It is a dimensionless number. This table shows some common refractive indices, ranging from air at 1.00, which has the lowest optical density, to diamond at 2.42, which has a very high optical density. To calculate bending angles, first identify the given angle and the refractive index. Then, rearrange Snell's law to solve for the sine of the refracted angle, and use the inverse sine function to find the final angle value. This chart compares optical densities. A higher refractive index indicates that light travels significantly slower and bends more when entering that material. Let's walk through a calculation. If light hits glass with a refractive index of 1.5 at a 30-degree incident angle, we use Snell's law. Solving for the sine of the angle of refraction gives us approximately 0.333, resulting in a refraction angle of 19.5 degrees. Next, we explore the critical angle, a fascinating phenomenon where refraction turns into reflection. When light travels from a dense medium to a less dense one, it bends away from the normal. As we increase the incident angle, the light bends further until it eventually skims right along the surface boundary. There are 3 stages of incidence. If the angle is less than the critical angle, we get standard refraction. When the angle equals the critical point, the light skims the surface at 90 degrees. If the angle exceeds this, total internal reflection occurs. The critical angle depends solely on the refractive index of the material relative to the surrounding air. Remember that a higher refractive index results in a smaller critical angle. For example, diamond, with its high refractive index of 2.42, has a very small critical angle of just 24.4 degrees, making it incredibly effective at trapping light. For total internal reflection to occur, 2 conditions must be met. Light must travel from a more optically dense to a less optically dense medium, and the angle of incidence must be greater than the critical angle. Now let's look at some real-world applications and phenomena of total internal reflection. Total internal reflection provides NEAR 100% efficiency, unlike standard mirrors which lose some light to absorption. Because no energy is lost to refraction, it is the ideal principle for carrying signals over long distances. This principle is also behind the sparkle of gems. Diamonds are cut so that light entering the top is trapped by multiple internal reflections, creating the brilliant shine we admire. Moving on to practical applications like periscopes and fiber optics. Right-angled prisms are commonly used to turn light by 90 or 180 degrees. Because the light hits the back surface at an angle greater than the critical angle for glass, it reflects perfectly, offering higher clarity and durability than a standard mirror. Another related phenomenon is the dispersion of white light. Because different colors have different wavelengths, they travel at different speeds in glass and therefore bend at different angles, creating the visible spectrum. As a result, red light, having the longest wavelength, bends the least, while violet light, with the shortest wavelength, bends the most. This process is responsible for the rainbow effect. An optical fiber consists of a very thin glass core surrounded by a layer called cladding. A crucial requirement is that the refractive index of the core must be higher than the cladding to allow for total internal reflection at the boundary. Optical fibers offer significant advantages for data transmission. Information is sent as pulses of light at near the speed of light. Total internal reflection ensures low loss even when fibers are bent, and one fiber can carry vastly more data than traditional copper wire. Optical fibers are also essential in medical technology, such as in endoscopes. These devices use bundles of fibers to see inside the body. One bundle carries light into the body to illuminate tissues, while another carries the reflected image back to a camera. This concludes our summary for week 2. We have covered the basics of refraction, the refractive index, the critical angle, the requirements for total internal reflection, and how these principles allow optical fibers to transmit data. Prepare for our laboratory session tomorrow. To test your knowledge, consider: if light enters a medium and speeds up, which way does it bend? Why does cladding have a lower refractive index than the core? And how would you calculate the critical angle for a material with an index of 2.0? Thank you for watching this lesson note on light waves. This completes our study module for Year 11 Physics. This video utilized various image sources to illustrate the concepts of refraction, Snell's law, and light dispersion. References include educational resources from YouTube, ePhotonics, Vids, and other physics study sites. Additional references for this video include visual materials provided by Wikipedia for light dispersion, Mead Optics for fiber fundamentals, and the American Gastroenterological Association for medical endoscopy imagery.